Watch this next shot closely, and you'll see what I mean about torsion bar suspension. Notice there's no slide nor sway in the turn, even at this blistering speed. You have perfect control. All the starters at Indianapolis since 1953 have been equipped with some type of torsion bar suspension. Looks as if that's about all on this reel.
You got room for another customer?
Hi, Tom. Turn on the lights and come on in. This is Helen.
How do you do?
How do you do?
And Carl.
Carl,
Mr. and Mrs. Bowman.
Tom, I'm very glad to know you, I'm sure.
And this is Tom Taylor, another automobile bug like me.
So Harvey's found a new audience for his home movies.
He has a wonderful collection. We were enjoying every minute of it.
All I did was mention this new torsion suspension I've heard so much about. Man, I sure pulled the trigger. I didn't know the gun was loaded.
You really put your foot in it now. I'm just an amateur. Tom's an authority on the subject. He's one of the automotive engineers who developed and perfected the first torsion bar suspension on a passenger car in this country.
Well, I don't get the point of this torsion bar gadget. I don't want to go racing around corners at 90 miles an hour. I want a car that's comfortable and safe and reliable. A big, roomy car I can relax in with a powerful engine and good brakes. So where does this torsion bar business fit in?
I was merely showing that the racers have proved that torsion bar suspension gives the best possible control of a car.
I know what Helen's driving at, and she's right. She'd probably have gotten your point if you'd started way back at the beginning.
I guess you're right at that. Go ahead, you tell it.
Well, you know the story as well as I do, Harvey. Cars have always been your hobby.
But they've been your bread and butter for a good many years. Why, you're part of the story.
Hey, fellas, let's quit passing the buck.
Yes, you said it started way back. What did you mean?
Well, a moment ago you said you wanted comfort in your car. What we in the automobile industry call a smooth, soft ride. Look over here. These old beauties were some of the best of their time, but they rode like buckboards, jarred the living daylights out of their passengers. So from the very beginning, automotive research and engineering faced the problem of developing a softer ride. They used buggy springs and wagon springs, crosswise of the chassis and lengthwise of it. As early as 1910, our company installed shock absorbers as standard equipment on this model. And of course, each year cars were being improved to provide more power and performance. But practically everything that made the ride softer decreased the load carrying capacity and increased the car's tendency to pitch and bottom. And the faster a car could go, the more hazardous the soft ride became. By the 1930s, just about when I started with the company, we had engineered and developed a manual ride control so the driver could adjust the ride to the road and the rate of travel. The need for this compromise indicates the dilemma automotive engineers faced. Soft ride versus control. In other words, what price? Comfort. To get the soft, easy ride the customers demanded, they had to compromise safety, stability, and control.
Well, I don't see where all this is leading. My car seems to ride quite comfortably, and well, I never have any feeling that it's out of control.
In a sense, you're right. Especially in good driving conditions, on smooth roads with gentle curves. My point is, from about the mid-30s until a few years ago, automotive engineers fought the battle of comfort versus control year after year. Inevitably, of course, they arrived at some fair compromises. But consider the disadvantages of conventional suspension that still existed in even the finest cars up to a couple of years ago. What happens when you fill the back seat with passengers and the trunk with luggage?
Why, the back end sinks down and the front end comes up.
Right. This changes the steering alignment and decreases the stability of the car. Furthermore, at night, they make your headlights ride so high they're not safe for you, and they blind the oncoming traffic. And when you have to accelerate fast, the same thing happens. Front end up, back end down. Let's say you're going up and over a railroad grade crossing. The back end pitches up, then slams down and hits bottom. Or you come to a dip in the road. The back end hits bottom, then pitches up and out.
You know, one time I threw the children, the dog, and some packages right off the back seat on the floor, just that way.
When you go around a corner, even at moderate speed, the front end dips and the car tends to roll. Whenever your car's weight shifts off balance in any direction, you're losing control. When you have to make a hard stop, what happens?
The car pitches forward, of course. And if you're on slippery pavement, well...
And obviously, as we increase horsepower and speed, these control factors become even more critical. And no matter what they do to improve the conventional types of suspension, in which the front wheels and rear wheels are independent of each other, these things we've been talking about can't be overcome. Here's why. When you hit a bump in the road, a chain of 4 reactions takes place. The front wheels go up, then come down. Then the back wheels go up and come down. At normal road speeds, the front end is still dropping as the rear end is rising. This throws the back end higher, and of course it comes down harder, hitting bottom frequently.
So where does this new torsion bar suspension idea fit into the picture?
I'm getting to that.
That's where Tom here and the men working with him in research and engineering scooped the rest of the automobile industry.
Scores of our engineers worked on it. Don't forget, we had the finest equipment, facilities, and technicians to work with, and a tradition of leadership in research and engineering that dates back to the early part of the century. We reasoned this way. Further attempts to reconcile the comfort versus control dilemma by merely improving conventional suspension systems could result only in minor improvements. But if we could employ an entirely new suspension principle that would give a soft ride and still keep the control already obtained in the race cars, well, we could have our cake and eat it too.
And that's just what they did.
Well, just what did they do?
Maybe I can show you. Harvey, how are you coming with that scale model chassis you were building for me?
Just about done with it. Need some touching up yet.
Man, you've done a beautiful job.
Harvey, that's marvelous.
It really is beautiful.
This shows the perfected torsion level suspension system. These long white rods are the main torsion bars.
Where are the springs?
The 2 main torsion bars are the springs.
I hope you'll pardon my feminine mind, but before we go any farther, just what is a torsion bar?
Well, torsion means twist. A torsion bar is a rod of spring steel that will twist when loaded, then untwist, or spring back to its original condition when unloaded.
Oh, I see what you mean. The spring is in the twist or the torsion of the bar.
Right. And here's the key to the system. On each side, the front wheel and the rear wheel are linked together by a main torsion bar so that they work together as a team. With this system, when a front wheel goes up or down, this front linkage twists or loads the front end of the torsion bar one way or the other. And when a rear wheel goes up or down, this linkage twists or loads the rear end of the torsion bar one way or the other. Of course, when either end of the bar is loaded, it twists the other end and operates the linkage there. So the front and rear wheel work together simultaneously. When the front wheel hits a bump, it loads the main torsion bar, which instantly transmits an equal loading to the rear wheel. As the front wheel comes down again, it twists the main torsion bar in the opposite direction, causing an instant and equal reaction at the rear. As the rear wheel goes over the same bump, it twists the bar first one way, then the other, causing an equal and simultaneous loading of the front wheel. Consequently, in a car equipped with torsion bar suspension, the car raises and lowers uniformly front and rear. There's hardly any pitch, and the car literally floats over bumps and holes. When a car comes to a hard stop, its weight shifts forward, and the front end wants to dip down. But remember, the rear axle torque arms are instantly loaded the same way, so the whole car squats down with very little pitch. On the other hand, when accelerating away from a stop, which tends to lower the rear and raise the front, the rear axle torque reaction tends to raise the rear end of the car to keep it level. What keeps the car level when taking a corner? It's because we use the force, which makes an ordinary car sway, to actually stiffen the spring action of our torsion bar. You see, this torsion bar gives us the softest spring action when its full length is used to take the shock of a bump. The bump loads only one end of the bar at a time. But when turning a corner, the bar is loaded from both ends at the same time, front and rear wheel. So only one half of its length acts like a spring for each wheel. This momentary stiffening of the spring action is what keeps the car level on corners. Another thing, this new torsion bar suspension system automatically levels the car when the load is changed. That is, when more passengers or baggage are added. These two short torsion bars and this electric motor actually do the leveling. When the rear end of the car is loaded or unloaded, the levelizer mechanism starts automatically. A built-in time delay keeps it from working until it knows that this load change is not just another bump. After several seconds, the mechanism levels the car. The load levelizer automatically keeps the car within 5/8 inch of level at all times. The best way to appreciate the sure-footed control of this new torsion level ride is to see it in action. Compare it with a car that has no torsion bar suspension nor load levelizer. A car we thought was tops only a couple of years ago. With our torsion level ride, as we call it, we can have both comfort and control. We can have our cake and eat it too.
Yes, I see what you mean, all right.
You must have a perfectly fascinating job to design and develop things like this.
It never gets monotonous, that's for sure. There's the constant challenge to make one new improvement on top of another. For instance, the elimination of the shift lever from transmission systems.
The what?
How can you drive without it?
Up until recently, even the so-called automatic transmissions have not been completely automatic. In this day and age, a truly automatic transmission system should respond to an electronic control at the touch of a fingertip. It should be as simple and easy to operate as push-button radios and home appliances. So our engineers have designed and developed an automatic push-button selector that controls our automatic transmission by an electronic device, as easy as turning on a light. It gives you instantaneous drive range selection at the touch of a finger. Touch the button, and away you go. Truly automatic motoring.
What a wonderful convenience. Real touch and go driving.
There's nothing like it. Puts an exciting new sensation in driving. Like taking off on a trip to the moon.
What happens if you accidentally push the wrong button?
It's foolproof. An automatic safety control built right into the electronic selector cancels your mistake.
Have you figured out how to eliminate the driver yet?
Sometimes solving one problem gives us the answer to another. For instance, drivers like the ease and convenience of an automatic transmission. But they also want the gas mileage that Overdrive gives. So one of the greatest improvements we could make would be to build the economy of Overdrive into our automatic transmission.
Well, how come that's never been done before?
Because the combination is mighty hard to do. To achieve the economy of a slower operating engine at a given car speed, it required 3 elements in the right combination. We had to have an ideal engine, transmission, rear axle combination. A numerically low ratio that called for exceptionally high torque in the engine. Fortunately, our engine designers were Johnny on the spot with the answer. Their problem had been to develop and build the most powerful engine with the highest torque ever delivered at the rear wheel in a passenger car. As a result, we got the ideal power ratio we need for overdrive economy in an automatic transmission. You have to see this new combination on the Proving Grounds to appreciate the results it achieves. It provides a blistering getaway from a standstill. It has tremendous reserve torque for climbing steep grades. And the new economy of overdrive in our automatic transmission, plus our push-button control, are an engineer's dream come true. So you see, we were able to improve our automatic transmission and rear axle ratio to build overdrive economy into them by building an engine that delivers maximum torque, efficiency, and fuel economy.
Boy, that sounds like a wonderful combination.
Here's another spot where there was room for improvement. The conventional differential. Why? Well, if you've ever been caught in soft sand or mud, you'll know what I mean. The one rear wheel that's in the hole just spins and digs itself in deeper, while the other rear wheel stands idle, and you're stuck. This is the path of the power through the old differential. Following the line of least resistance, it always went to the spinning wheel that has no traction. Now, to overcome this, our engineers succeeded in designing a simple method of transferring the power through a new kind of differential to the wheel that's on firm ground and has traction. As a result, the car with the new twin traction differential has less of a tendency to dig itself into sand or mud. But in case your car should be driven into a hole or a deep rut where the traction is poor, the moment one rear wheel begins to lose traction by spinning, twin traction instantly transfers the power to the other wheel, and out you go. On rough washboard roads, where sometimes the rear wheel bounces and spins when power is applied, this new instantaneous power transfer from the bouncing wheel to the wheel that has good traction avoids that chattering spin. It makes a smoother and safer turn on rough or slippery pavements. And on winter ice, where the old differential would spin one wheel helplessly while the car stands still, now with twin traction, you not only move off the ice easily, you have enough power and enough traction to pull 5 cars off the ice. This is the first great improvement in rear axle design since we introduced the hypoid gear rear axle in the early 20s.
What else have you up your sleeve?
Oh, we're working on all kinds of developments we can't even talk about yet. You see, in automotive research and engineering, many of us are planning as much as 5 to 10 years ahead.
We've got to get going. I promised Beverly and Jean we'd meet them at the club just about now.
Good.
Give me just a couple of moments to fix my powder.
Settle down, boys. We'll be a while yet.
There's no point in taking both cars. We're all coming back here afterward. Which one shall it be?
Let's take this one.
Okay, we'll take your car and leave mine here.
Who's going to drive?
You've already decided that, haven't you?
Say, Harv, let you and I sit in the back for a change just to see how it feels.
Okay by me.
Wonderful experience.
Hey, mister, you want to see something really terrific? Watch. How about that, huh?
What'll they think of next?